Hi everyone, welcome to ECE10B Foundations of Analog and Digital Circuits and System. I'm your instructor for this quarter. My name is Loai Salem. I received my PhD from the University of California, San Diego in 2018. I have my research group. Essentially, this is a website for my research group, and my work basically is in power electronics and power management integrated circuits. Here are some examples. In my research group we build both integrated circuits, proof of concept, as well as printed circuit board level proof of concept of new ideas in power electronics and power management ideas or research. So, what is the objective of 10B? Well, in 10A, essentially we learn the basic analysis laws and rules of circuits, Kirchhoff's voltage law, Kirchhoff's current law, voltage dividers, current dividers, and all these basic ideas, Thevenin, Norton theorems, and superposition theorem. In 10B, basically we focus on using transistors, how to design circuits containing transistors. Mainly or specifically how to design logic gates, amplifiers, and how to use different transistors to realize these electronic component or electronic circuits. Also, another or the second part of the course focuses on the analysis and design of RC and RL circuits. We're going to introduce what's a capacitor, what's an inductor, and how. And essentially, we're going to analyze basic RL and RC circuits. I already enabled Canvas. You will find all the information, all the details you need to look for. You need to know about the course, which textbook to use, which, by the way, is called Foundations of Analog and Digital Electronic Circuit by Lang and Gower. The syllabus essentially, and when is the midterm, when is the final date exam. Homeworks will be uploaded weekly to Canvas, and essentially going to provide your answers using e-grades Gradescope. Any announcement will be on Canvas as well. Our TA is Farzan Rizai, and that's his email. We're going to, he's still choosing a time for his office hours. So for the class mode, essentially, I'm going to record lectures, post them on the day of Tuesday or Thursday or before that. So please watch the videos for the lecture, and then we're going to meet in the classroom at the class time. If you have any questions or for any further discussion of the details of the lecture, you can come to the classroom and we can discuss any detail or answer any questions you might have. So technically, the lectures on Tuesday and Thursday will be both the office hour and for further discussion. You don't have to attend the classroom if you don't want to. I don't take attendance, and mainly it's like an office hour if you have any questions on the lecture or homework. However, if out of students, they ask me for recommendation letters, so if you want to have a good letter of recommendations, better to show up regularly so that I get familiar with you and your performance in the class. Usually I do my own schematics, but sometimes I might borrow figures from the textbook that we are using for this class. I think one second. Let's see, go to Canvas. I think the chapters. I'm just making sure I put all the details, required details on Canvas. Let's see. Yeah, so We are going to cover mainly from this textbook. We're going to cover chapter 6 to 10 as well as chapter 15. So 6 to 10 and 15. That's what this course will focus on from this textbook. All right. So for 10BL, the lab part of 10B. So 10B is just lectures and homeworks. Analytical, we learn the theories, the analysis of how to design transistor circuits, whether it's digital or analog, as well as RC and RL circuits. The 10BL is the lab part or lab portion of 10B, and it consists of 6 labs starting from 0. So technically 7 labs, but I like to make lab 0 is basically a simulation task using LT Spice, so you don't need to be physically going to the lab in Harold Frank Hall. So this is the location for the lab. You don't need to show up for lab 0. You can just do it from your home because it's a simulation using LT Spice. And then starting from lab 1 up to lab 6, you need to conduct experiments. You will have a lab manual. The TA is going to direct you and give you some background, and then you need to perform experiments and collect data and then submit a report, and that's basically what will define the grade for 10BL. It's just the reports that you submit to grade school for the lab. You need to attend the lab again because you need to collect the data. However, you can work in groups of 2 students, not more. And you can share components. Okay, so for today's lecture, basically these are the sections that this lecture is going to cover: the switch, logic function using switches, the MOSFET device and its switch model, the switch resistance model of the MOSFET, and then the MOSFET switch implementation of logic gates. In this video, we'll see essentially what is a logic gate, and we are going to explore the basic logic function or logic gates as well as their truth tables. So first of all, what's a logic gate? Well, a logic gate is basically an electronic circuit that performs a logical function. For example, say we want to design a light for a garage door. We have a garage, and for this garage we have a door, and basically we want to design a circuit for the light bulb at the garage door such that it turns on when it's dark, turns on automatically when it's dark, and there is a motion in front. So once the car arrives in the front of the garage, essentially the light bulb, or there is a motion in front of the garage, and it's dark or nighttime, the light bulb is going to turn on. So as you can see, if it is dark and there is motion, then turn on the light bulb. So how to design a circuit that's going to implement this logical function is called a logic gate, basically. So how to design a circuit that performs this simple logical expression? Well, we can use 2 switches in series. And here is the light bulb. And then we have an input battery or whatever the voltage source. And we connect 2 switches in series. So we're going to have a sensor, a light sensor. Assume that the light sensor essentially is going to output logic 1, when it's dark. And we'll have another sensor, a motion sensor, that's going to output logic 1 if there is motion. So once it's dark, the light sensor is going to produce 1, logical 1, and when there is motion, the motion sensor essentially is going to produce logic 1. And assume that these switches are going to turn on when you apply on their control input logic 1. So once it's dark, this switch is going to turn on. And when there is motion, the second switch is going to turn on. And so the light bulb is going to give light, or essentially is going to turn on. Okay, so circuits that implement logical expressions are basically called logic or logic gates. And some of the basic gates, or some of the basic logic gates, we have the AND function, the OR function, and their complements, and I'm going to explain that. NAND function and NOR function. Essentially we just add N in front of OR N in front of AND. So if we look at the logic function AND, and we look at, first of all, its symbol is going to look like this. It has two inputs and an output, say Y, and the inputs say A and B. The OR function looks like this. Y, two inputs, A and B. Now, let's look at what is the, for the AND function, and let's remember the garage door light, automatic light circuits that I just discussed. We had, for the AND logic function, if we have four possibilities. Let's say we have the light sensor, and we said if it's dark, it's going to output 1. If it's if there's light, it's going to produce 0, logic 0. And then the motion sensor, and then we have the output of the gate or the circuit. So as you can see, since we have two inputs and each input can be either 0 or 1, right? So we have four possibilities: 0, 0, 1, 0, 1, 0, 1, 1. So if it's daytime, so the first 0, and there is no motion, then the AND is going to produce 0. The AND gate is going to produce 0. If it's daytime and there is motion, there is no need to turn on the light, so produce 0. If it's nighttime but there is no motion, no one there, so also there is no need to turn on the light, so the AND gate is going to produce 0. If it's dark and there is motion, this is the only time that the light bulb is going to be turned on. And as I mentioned, a simple way to implement this function, just put two switches in series. Now let's look at the OR logic function. So this is called the truth table for the AND gate. Let's look at the truth table for the OR gate. And as I mentioned, what's a logic gate, what's an OR gate, is essentially a circuit that implements the logic OR. And basically this means if we have two inputs A and B, imagine them coming from sensor, and there's some system we need to design an OR gate for, and then we have the output Y. Again, two inputs, and each input is digital, so it can take either 0 or 1. So we have four possibilities: 0, 0, 1, 0, 0, 1, 1, 1. And in the OR function, or if we go back to the AND function, the output is 1 only when both inputs are true or 1. Otherwise, the outputs are 0. On the other hand, for the OR function, as the name suggests, if either one is logic 1, then the output is going to be 1. The only time that the OR gate is going to produce 0 if the two inputs are 0, the OR output is 0. Otherwise, if either input is logic 1, its output is going to be 1. Okay? So notice the difference between the OR and the AND gate. The AND gate produces 1 only when both inputs are 1. The OR function produces 0 only when both inputs are 0. Now, the NAND function, one second. The NAND function is just the complement of the AND logic gate. And it looks like an AND gate, but we add a bubble at the input, and this means essentially not. It's as if you had added an inverter at the output of the AND gate. And so an inverter is essentially inverses if the inverter essentially will produce, if the input is logic 1, it will produce 0. If the input is 0, it will produce 1. It just inverts the input, okay, as the name suggests. So the NAND, as I mentioned, is just an AND gate followed by an inverter or a NOT gate. So if we assume this is AB, this is Y. Again, we have 4 possibilities. So it will be essentially this output just inverted. So it will be 1, 1, 1, 0. And so the output is only 0 when both inputs are 1. Now for the NOR function, as I mentioned, not OR, so essentially it would look like an OR gate, but we just add an inverter afterwards. Or basically we just put a bubble. And then we have the truth table, AB. We have 0, 0, 1, 0, 0, 1, 1, 1. And so its output will be essentially the OR output just inverted. So it will be 1, 0, 0, 0. And so the output is the only time its output is true when both inputs are 0. Now we're going to see how to realize a switch, and basically the way to realize a switch is to use a transistor. So when I mentioned the AND gate, or the example for the garage door, the garage door light, we wanted the light to turn on if it is dark outside and there is motion. If it is daytime, there is no need to turn on the light bulb at the garage door. If there is no motion and it's dark, there is no need to turn on the light bulb. Only if it's dark and there is motion, then turn on the garage door light bulb, okay? And to implement this function, we can just simply use 2 switches, as I mentioned, in series. Then we have the light bulb. And the input voltage source. And so when it's dark, the motion sensor, the light sensor is going to produce 1, logic 1, when it's dark outside. And we have a second motion sensor, or the second sensor essentially detects motion and produces logic 1 when there is motion. So if it's dark and there's motion, both are going to turn on, and which will turn on the light bulb. So the question now is how to realize these switches. course, you can use a relay, but nowadays a better way to realize a switch is using a transistor. And a very simple transistor, the symbol for a transistor is as shown here. It's a 3-terminal device. It has 3 terminals, just like a switch. A switch has 3 terminals: left terminal, right terminal, and the control input. For a transistor, it has gate input, drain input, and source terminal. So gate terminal, drain terminal, and source terminal. 3-terminal device. And this symbol is particularly for a specific type of transistor called MOSFET. Or more particularly is N-type or N-channel MOSFET. And MOSFET stands for metal oxide semiconductor field effect transistor. So this symbol is for N-type or N-channel MOSFET, and for short we can just say NMOS. Another note here is if current is flowing, or if current in transistor is flowing from top to bottom, then the top terminal is going to be drain, the bottom terminal is going to be source. On the other hand, if the current is flowing from bottom to top, this means in that case we will find that the bottom terminal is going to be the drain, the top terminal is going to be the source. And of course, if current is flowing from top to bottom, this means the drain terminal has higher potential or higher voltage than the bottom terminal or the source terminal. So in a nutshell, an NMOS transistor or a MOSFET essentially is allow current to flow in both directions, top to bottom or bottom to top. If it flows from top to bottom, this means the top terminal has higher potential than the bottom terminal. If it flows from bottom to top, this means the bottom terminal will have higher potential than the top terminal. And finally, if the current is flowing from top to bottom, this means the top terminal, we call it the drain, the bottom terminal, we label it as the source. On the other hand, if current is flowing from bottom to top, then we're going to label the bottom terminal as the drain and the top terminal as the source. On the other hand, the gate is always a gate. It doesn't, there's no exchange with the drain or source. Another thing is, we call the current that's flowing in the transistor, say I, we call it IDS, current from drain to source, IDS, okay? And this is the arrow, for example. This is the drain terminal, source. The gate current, we call it IG, and the gate current in our case is typically very small and actually almost zero, okay? As this symbol suggests, it's isolated. So no current is going to flow in this direction. Okay, so as I mentioned, what's a transistor at the end of the day? It's basically a switch. When we apply logic 1, at the gate, just as in this example, when the light sensor produces 1 when it's dark outside, logic 1, this logic 1 essentially is going to turn on the transistor, so essentially it's going to more or less behave as a short circuit, connecting the drain to the source. On the other hand, if the input, if the gate voltage, or sorry, the gate input is logic 0, we'll find that the transistor will behave as an open circuit. So it's basically a switch. If you apply at the gate logic 1, it will act as a short circuit connecting the drain to source. On the other hand, if you apply logic 0, it's going to be an open circuit, just like a typical relay or a switch. One last point for the symbol, typically the source terminal is indicated by an arrow. Okay, sometimes we can just draw the transistor, the NMOS transistor, the N-type MOSFET. We can draw it without the arrow, and in some data sheets or in some textbook, we will see that the source terminal is indicated by an arrow. A little more detail about a transistor or a MOSFET. We'll find that, as I mentioned, logic 1, when I say we apply logic 1 at the input, this means we apply a specific amount of voltage, say 5 volt. So when I plotted or essentially sketched the truth table for a gate A, B, and Y, and we said we have 4 possibilities: 0, 0, 1, 0, 0, 1, 1, 1. And then say it's an AND gate, so it will produce 1 only when both inputs are 1, otherwise it's always 0. What's 1 and what is 0? At the end of the day, we are building circuits. This is a circuit, right? So what I mean, the motion sensor produces, or the light sensor essentially produces logic 1. What I mean by that, logic 1 maps to a specific amount of voltage. Say, for example, typically 5 volt. Logic 0 maps to 0 volt. Okay, so we can actually sketch this table, truth table for the AND gate, as follows by mapping the logical values to their actual voltage values. 0, 0 is 0 volt, 0 volt. 1 is going to be 5 volt and 0. Then 0, 5 volt, 5 volt, 5 volt. So that's exactly what happened. So if we bring a gate, a logic gate, and we try to test it in the lab, and you want to verify its functionality, you bring a power supply, which is a voltage source, or in the voltage mode, so essentially act as a voltage source, and then you try to the different combinations 0, 0, and see, measure the output voltage. You'll find it 0 volt. Then you apply 5 volt 0, so this is 5 volt. You apply here 5 volt and here 0. Say you have a 2-channel power supply, and then the output is going to be 0, and so on for the remaining values. And the only time you'll find the gate is going to produce 5 volt. If both inputs are 5 volt, then you will find the output of the gate is 5 volt. Now, if we as I mentioned, a transistor is basically what? A switch. However, this switch, to turn it on, you need to apply a voltage that's larger than a threshold value. So basically, if you want to turn on the transistor and make it connect the drain to the source, you need the gate to source voltage, this voltage, and we give it the symbol V capital, GS, VGS. So you want VGS to be larger than a specific voltage value. We call it the threshold voltage. The threshold voltage. And typically the threshold voltage is about, say, 1 volt, 0.7 volt. So when you apply logic 1 at the input, which is 5 volt, of course 5 volt is going to be higher than the 0.7 volt, which will make the transistor connect the drain or short the drain to the source. Turn on, essentially. And this is, by the way, we call it on state. On the other hand, if VGS is less than the threshold voltage, we'll find that the transistor will act as an open circuit, and we call this off state. All right. Now, so in this slide, we talked about threshold voltage, and the bottom line is a transistor to turn it on, since it behave as a switch, to turn it on, you need to make sure that the difference between the gate and source is higher than a threshold value. And essentially, so VGS must be larger than VT in order for the transistor to turn on, otherwise the transistor will be off. A second detail is that when the transistor turns on, it actually doesn't behave as a short circuit. It connects the drain to source, but it has a finite amount of equivalent on resistance or on state resistance. On state. So the point here is it doesn't apply 0 ohm resistance, which is a short circuit. A short circuit is basically a resistor of 0 resistance. It doesn't apply a short circuit between a drain source. It actually applies or essentially the path between the drain and source that it connects, it has a finite amount of equivalent on resistance, R on. And in this case, we'll see that when VGS is larger than or equal to the threshold voltage, the transistor connects the drain to the source, and there's a finite equivalent on resistance between the drain and source. On the other hand, if VGS is less than the threshold voltage, the MOSFET will behave, or the NMOS will behave as an open circuit. Now let's look at the current or drive an expression for the current from drain to source. Well, we have two scenarios. This is, by the way, called on state. This is called off state. We have two scenarios. Either the gate to source voltage, VGS, is larger than the threshold voltage, VT, or VGS is less than the threshold voltage. If it's larger than the threshold voltage, we will have a finite on resistance between the drain and source, and so the current will basically be what will be the voltage difference between the drain and source, which we called V capital DS, VDS. So it will be VDS divided by R on. That's the current. The voltage difference between drain and source divided by the resistance from Ohm's law. On the other hand, if the VGS is less than the threshold voltage, then it will act as an open circuit. So essentially, the current IDS, the drain to source current, is going to be 0. Now, this is a more practical example, or an actual IC integrated circuit that basically contain 4 NMOS transistors. 4 NMOS transistors. Of course, if you need more details, you can go to DGKey. DGKey is a well-known supplier for electronic components, and search for the ALD1106, and you will find it's more details and its data sheets and more of the details and all other related information. And as you can see, we have how many? 1, 2, 3, 4, 5, 6, 7 pins, and this is how it looks like. Now, one thing about this integrated circuit that contain 4 NMOS transistors. If we look inside the datasheet, first of all, it says quad N channel or N type matched pair MOSFET array. By the way, the datasheet indicate 2 types, either AD1106 or 316. This IC that's 1116 is dual in channel, but in this specific example I'm talking about this one, which is 1106, that contain 4 NMOS transistors. So if we look at this IC, if we look in the data sheet, you will find that it mentions the threshold voltage, VT. And as you can see, typically is 0.7 volt. And of course, when you manufacture the manufacture of this IC, right, in mass production, there is some tolerance. So the threshold voltage will have a range. Maximum or worst case is 1 volt, best case is 0.4, but we design for the typical case. Now, also another piece of information in the datasheet is the drain source on resistant or on state resistant. They quote in the datasheet RDS on, or basically R on, that I mentioned. When the transistor is on, basically it applies connects the drain to source via a resistance, not a short circuit, or its channel basically has a finite amount of equivalent on resistance. And for this transistor, for any of these transistors, you will find that the equivalent on resistance is 350 ohms in the typical condition, or typically, but it in worst case is 500 ohm. And as I mentioned, we design for the typical case. And an important information, as we're going to discuss later on, when the transistor turns on, right, it connects the drain to source via a finite amount of resistance R on. In this case, is 350 ohm. This 350 ohm actually, its value depends on the voltage difference between the gate and source. So you will see in the datasheet says the condition here, the gate to source voltage is 5 volt. So when the gate to source voltage is 5 volt, the equivalent on resistance 350 ohm. And it will become clearer later on that when we reduce the gate to source voltage, you will find that the equivalent on resistance increases. So if VGS say 1 volt instead of 5, you will find instead of having an on state resistance of 350 ohm, it might be say 1500 or 3000 ohm. Okay, so remember that the equivalent on state resistance depends on the gate to source voltage, or at least when you look in the datasheet, make sure to look what is the value of the gate to source voltage at which the equivalent on state resistance is measured. And so if we go back to our example of the garage door light bulb, we want to turn on the light bulb only if it's dark and there is motion. So to implement that, we're going to connect 2 transistors in series. Then we have the input voltage source. So if it's dark, the light sensor will produce 5 volt, which will turn on the first transistor. And if there is motion, essentially the motion sensor is going to produce 5 volt, which will turn on the second transistor, and the voltage will be applied across the light bulb. But if we sketch in the on state, if both transistors are in the on state, if we plot or sketch the equivalent circuit, we'll find that we have R on of the first transistor in series with R on of the second transistor, and then we have the light bulb. So how to implement an inverter? As we know, an inverter or a NOT gate, this is the symbol for an inverter. Say the input is X, the output is Y, and we have 2 states, 0, 1. Essentially it inverts. If the input is 0, it produces 1. If the input is 1, it produces 0. So how to implement this gate using a transistor? Well, The simplest implementation is basically to connect an NMOS transistor in series with a resistor, a pull-up resistor. And the input voltage is basically, or the supply voltage is VDD. When the schematic's plotted this way, and the supply is indicated just with a horizontal line, and then we label it with the supply voltage value, or the supply voltage name, this means this is equivalent exactly to, you have a voltage source, its value is equal to VDD, and then you have a resistor R, a MOSFET, then MOS, and the bottom node is the ground node. So instead of sketching the supply or the voltage source explicitly, we just indicate it by a horizontal or a dash line. Then we have the input X for the gate. The output is taken from the drain terminal of the transistor. So this is the drain, this is the source, this is the gate. So this is going to be the output of the inverter Y. So how does it work? Well, if the input voltage is less than the threshold voltage of the transistor, we expect that the output will be what? Or first, we expect that the transistor is going to be open circuit. So what will happen? Well, this means the current that's in this resistor R, the current here, will be 0. And if current is 0, this means the voltage drop across this resistor will also be 0. And so this means Y, the voltage at Y node, is going to be equal to the supply voltage VDD, which is equivalent to logic 1. If say the supply voltage VDD is equal to 5 volt, so the output is going to be 5 volt. Okay, so when the input voltage is less than the threshold, the output is 1. On the other hand, or which essentially implements the first row in the truth table of a NOT gate or inverter function. So when the input is 0, which is less than the threshold voltage, the output is going to be logic 1, or essentially 5. On the other hand, if the input is 1, so we have the case that the input X is larger than the threshold voltage of the transistor, say 5 volt. If we apply 5 volt at the gate, what will happen? The transistor essentially will turn on, and as we said, is going to apply or connect the drain terminal, its drain terminal to its source terminal via its equivalent on resistance R on, and then we have the pull-up resistor. This is Y. So basically the output, if we assume R on is much smaller, or let's write the expression for it. So Y, from the voltage divider, we have 2 resistors. The input voltage is, or the supply voltage VDD. The output essentially will be VDD multiplied by R on divided over the sum of R and R on. And so if the resistor R, the pull-up resistor R, is much larger than R on, we'll find that Y essentially will be almost equal to 0 or the ground. Okay? And this implements the second row in the truth table for an inverter. So when the input is 1, this means, or 5 volt essentially, and the threshold voltage say of the transistor is 0.7 volt, we'll find that the transistor will turn on, apply R on, and essentially will bring Y to the ground node, assuming R, the resistor R, is way larger than the equivalent on resistance of the transistor. Okay, so let's try to sketch the voltage transfer, the input-output voltage transfer characteristic of the inverter that we just built. So we have a resistor, we have the NMOS, input is X, output is Y, supply is VDD. The voltage transfer characteristic, on the horizontal axis we're going to put the input X in volts. On the y-axis we're going to put the output of the inverter Y in volts. And let's see, well, as I mentioned, is if X is less than the threshold voltage of the transistor is open circuit, so essentially no current flows in the resistor, and Y essentially get connected to VDD, or Y essentially becomes equal to VDD. So for all values for all X values less than VT, the output is basically VDD. On the other hand, for values larger than, say this is VDD or 5 volt, for all these values that are larger than the threshold voltage, when X is larger than the threshold voltage or equal to the threshold voltage, essentially the transistor will turn on and will bring the node Y to the ground, assuming the resistor R is way larger in value than the equivalent on resistance of the transistor. So basically the output will be 0. And this will be the voltage transfer characteristic of the inverter that we just built. Now let's see how to implement the NAND gate using NMOS transistors. Well, as a reference, let's put the AND gate, or the NAND gate, sorry. Why? We said the NAND gate is just the inversion of the AND gate. The complement of the AND gate. And we know that the AND gate produces 1 when both inputs are 1. That's the only case. Otherwise it produces 0. So the NAND gate, the truth table for the NAND gate, which is the complement of the AND gate, will be basically 1, 1, 1, and 0. It will produce 0 only when both inputs are 1. Okay, so that make it clear. So how to realize it? Well, it's a gate or a circuit that produces 0 volts when both inputs are high, or basically 5 volts. So we can just connect two NMOS transistors in series to the ground. This is input A, this is input B. So when both are on, they will bring the node Y to the ground. Otherwise, the output should be 1. If either 1, if B is 0 or A is 0, essentially the pull down path is going to be open. And so we put a resistor at the top, a pull up resistor, so that it pulls up the output Y to VDD. And that's how to implement a NAND gate. So the NAND gate will be, as I just showed, 2 transistors in series. And from now on, to implement or to perform ANDing or NANDing, essentially, you connect 2 transistors in series. So this is R, this is input A, input B, and this is VDD. So this is how to implement an AND using NMOS transistors and a resistor. Now, if I want to implement an AND function, well, just cascade or connect this gate to an inverter, the inverter that we just built. The good thing is input is a transistor gate current is equal to 0, and this allows to cascade multiple gates. So we cascade in inverter to the NAND gate, so the output is going to be essentially the ANDing of A with B. At this node. Now for the NOR function, we said the NOR is a complement of the OR, and the OR function always produces 1, and the only time it produces 0 when both inputs are 0. So when both inputs are 0, a normal OR gate, an OR gate essentially will produce 0. For an OR, which is a complement, then it will produce 1 when both inputs are 0. On the other hand, if either input is 1 or both is 1, an OR gate is going to produce 1, so an OR gate will produce 0. So how to implement this? Well, for an AND, we connected 2 transistors in series. For an OR, we connect 2 transistors in parallel. Which makes sense. So if A is 1 or B is 1, the output will be pulled down to the ground. If A is 1 or B is 1, this transistor will turn on, or this transistor will turn on, which pulls down Y to the ground. Otherwise, we have a resistor, a pull-up resistor that pulls up the output Y to VDD. Okay, so if A is 1 or B is 1, these 3 cases, be pulled down to the ground. Otherwise, essentially both transistor A and transistor B will be open circuit, and so this resistor will pull up Y to VDD, and we get this case. All right, let's take now what I want you to remember. NANDing, or to perform NAND, you connect transistors in series. For NOR, you connect transistors in parallel. So if we have this function and we want to implement it using transistor, well, it's very simple. We're going to A and B, ANDed with B, we connect 2 transistors in series. A, B. Then we have OR C or D. This means we connect transistor C in parallel, another transistor D in parallel, and all these are connected to the ground. So we're going to pull the output Y to 0 in case C is 1, in case D is 1, or if A and B are together 1 at the same time. Otherwise, the output will be pulled up by the resistor R. Okay, so always ANDing, we just connect 2 transistors in series, ORing, we connect them in parallel to the output. Now let's look at, and of course we have the complement here, because as we said, NMOS transistor will pull the output to the ground. So at the end we have automatically inversion. If you are not convinced you can implement or essentially get the truth table for this function, and in this case we have or write the truth table for this function. In this case we have 3 inputs, so we have 8 possibilities. A, B, C, we have 0, 0, 0, 1, 2, 3, 4. Okay, and try all combinations. You will find that at the end of the day, this schematic does implement this function. Now let's look at how to implement the function on the right using transistors. We have A or B, okay, so we connect them in parallel. And then A or B is ANDed with C and D. So ANDing is connecting transistors in series. So transistor C will be in series and transistor D will be in series. And that's the only time the output will be connected to the ground. Okay, so A or B, we connect to transistor A in parallel with transistor B, then we end it with transistor C and D, we connect transistor C and D in series. Otherwise, the output is pulled up to the supply via the pull-up resistor R. Again, if you are not convinced, you can test or write the truth table for this circuit and you see that it's implementing this logic function exactly. And as I mentioned, if you wanna any of these function, you wanna remove this inversion, essentially just connect or cascade an inverter with the gate function.